Hello, Algebra 2 students. Today we're going to look at a topic that departs a little bit from our previous um, strain of thought, which was focusing mainly on the library of functions. We just finished up with polynomial functions. Now we know about bouncing, multiplicities, different types of end behaviors for snake functions, and functions that involve all kinds of different polynomial shapes. We've also, of course, looked at basic parabolas, which is also a polynomial. We looked at exponential functions and all those kinds of things. So before we continue further into our journey of the library of functions, I think it's important to address sequences, because sequences are important because, for one reason, your calculator and a machine in general can't hold an infinite amount of information in it. So it's not like it does what we do as human beings and refers to a memorized kind of shape of a function from the library when it draws a function when you type something into y equals. Instead, it does something with a sequence. So let me see if I can explain how it does that. So what we're going to look at first today is this note guide. So you should be following along with this note guide that you have as you're watching the video. So what a sequence is it's a function. It's a special kind of function. So a sequence specifically is a function that operates on the natural numbers. In other words, it maps the natural numbers. Let me move that up just a little bit. So the natural numbers are usually denoted with a capital script N. So usually there'll be like a little double bar right here, like the integers are script Z. So that's what a sequence is. It's just a function, just like any other function we've learned, except it's a really special type of function. It operates not on any number, because functions that we saw before, you could put anything into them. You could put 7.3 into them. You could put negative 11.35 into them. You could put pi into them, even irrational numbers. They were real valued functions. What we've got now is a sequence, and a sequence is a natural number valued function. In other words, it only works with the counting numbers. Those are the natural numbers right here. 1, 2, 3, 4, 5, etc. Oh man, I'm very good at highlighting, as you can tell. So that's what a sequence is. You can think of this object, a sequence, as, first of all, you can think of it as a list. Okay, so the easiest way to think of a sequence is just a list. It's expressing some kind of precise pattern in a very precise and easy to use way for mathematics and for machines. So sequences can be expressed in a variety of ways. So I wanted to really make a note here, and I'll just put it back up here at the top, that there's this difference in sequences which my students at the very beginning, before they have any experience, get confused a lot. So there are notations for sequences. On one hand, there's notations, and there'll be 3 of these, which we're going to be working with. There's also types of sequences. Just like there were types of functions in the library, like parabolas and exponentials, there's types of sequences, and they really actually correspond to some of those functions that you've already studied. So there's sequences, or ways to express sequences. Those are notations. And there's types of those sequences. Each type can be expressed 3 ways. So let's go and look at those 3 types, because that's pretty much the only ways you can ever see a sequence. So the simplest way to see a sequence is if it's just listed, so a finite listing of some sort. So my example here on this guy, and there should be, I'm going to get a little marker here and draw in. I meant to put a little comma right there as well. This sequence is, first term is 4, 13, 22, 31, 40, etc. That's my ellipses. That's a list, of course, so it's pretty simple to see that that's a list of stuff. So some of you might be wondering, but I thought you said a sequence operates on 1, 2, 3, 4, 5, the natural numbers. Those aren't 1, 2, 3, 4, 5. Well, that's very good. But I didn't say that these were the inputs. 1, 2, 3, 4, 5 are the inputs. The first term in this sequence is 4. Oh man, that's way too thick. Let's go and grab my pen. The second term in this sequence is 13. The third term in this sequence is 22. The fourth term in this sequence is 31. The fifth term is 40, and so forth. So the inputs are the natural numbers. The outputs can be pretty much anything. So that's what we have when we have list notation. So another kind of sequence notation that you'll run into very commonly is explicit notation. So an explicit formula or explicit notation looks something like this over here. It's got a sub n, that's how you say that, a sub n, and it's a formula just like f of x. So it's got all kinds of different rules. Looks like we have something with a parabola, something with a cubic function. And if you put 1 in, you get the first term by going 1 squared plus 1 cubed. So that would be 2 is the first term in that list. The final way that you can represent a sequence is like this example over here, where you have an a sub n as well, but a sub n refers to another a sub n expression. So this basically says the current nth term is double the previous term, because that's what a sub n minus 1 means, plus 2. And you have to be given a starting point in this kind of notation. This is called recursive sequence notation. Okay, so before we move on and actually start working with these notations, I thought we'd just go and think about how sequences relate to functions a little bit more in depth. So first of all, let's think about this sequence right down here. So how about this sequence right here? That should look familiar. In fact, if I called it a function, I bet you'd recognize it. It in fact is a function of the natural numbers. So what kind of function is that? I think you should recognize it. It's an exponential function. It has a base of 3, that's exponential growth, and it's 4 outside means it's shifted 4 up. So I'm going to shift it 4 up, mark my asymptote here. There's my asymptote and its exponential growth. Here we go, growing upwards. So there you go, there is your exponential function. So that's a function. That totally ignores the idea of a sequence. So if we thought of it not as a sequence but as a real valued function, it'd be an exponential, just like the blue curve I have right there. I guess I should have made this blue, but that's okay. So where does the sequence come into play? Well, the sequence comes into play by doing what a machine would do. A machine can't graph this the way that we did it based on our knowledge of the shape of an exponential function and transformations. It can just operate with one number at a time, like 1, and another number at a time, like 2, and another number, 3, 4, and it can deal with quite a few numbers, just not an infinite amount. So if you think of this as a sequence and go from the a sub n side over here, 1 would get plotted up here in this sequence. In fact, if you put 1 in, you get 3 times 1 plus 4 is 7, so that'd be 7. If you put 2 in, you get 3 squared plus 4 is 9 plus 4 is 13, so I don't think my curve is nearly steep enough, but you get the point that you're going to get just some discrete, specific spots on this function curve, and that is the sequence itself. So the calculator in a machine would basically just connect those dots together to draw the function for you. That's kind of what we're doing when we're working with sequences. All right, let's start getting into some problems. So the first problems here say just find the first 5 terms of each sequence. So that's what we're going to do. We're just going to work with the first 5 terms. And oh, I need to delete some more stuff, so give me a second here. Should have deleted these. This is kind of cheating. Okay, so our first 5 terms here, well, let's just do it one at a time. So a sub 1. A sub 1, we're going to plug 1 in right there. So that's going to be 1 minus 2. I hope you can do that without a calculator, but use 1 if you need to. That's negative 1. That's the first term. Okay, we're done. Let's look at the second term. The second term, we're going to plug 2 in for n, and we'll get this. So if you want to, you could pause the video right now and finish these up. So I think that's going to be 4 minus 4. That's 0. So then a sub 3. What's a sub 3 going to be? It's going to be 3 squared minus 2 times 3. That's going to be 9 minus 6. That's 3. Okay, and then a sub 4. It's going to be 4 squared minus 2 times 4. 16 minus 8. Or 8. And the fifth term, since they asked for 5, is going to be 25 minus 10. So notice I skipped a little bit of work on that one. It's going to be 15. So how do we turn this explicit notation, I hope you recognize that, into a list? Well, you say the first term is -1, second term is 0, then we've got 3, 8, 15, and so forth. There is the list form of that sequence. Let's look at the second one. The second one has a sub n, and it references a sub n minus 1, so hopefully you guessed that this is recursive notation. So in recursive notation, they always have to give you a starting point, so they already provided us with a launch pad, and they gave us the first term is -2. That's the launch pad. So you could do this the same kind of plug and chug way. I'll do that for the first couple terms. So the second term is going to be 3 times 2, pop it right in for n, and you're going to get 2 minus 1 right here, which is going to be 3. 2 minus 1 is 1. And then do you know a sub 1? Well, yeah, you do. You know it's -2. So it's 3 times -2, which is -6. All right, let's plug and chug again. So we're going to go 3 times a, putting the 3 in for n. So that's 3a sub 2. A sub 2 is, of course, oh, we just had that. That's -6. This is going to be -18. And after you've done a couple, you might start getting the hang of this and go, hey, wait a second. This just says the fourth term. If I put 4 there, I'm going to get 3. That's a terrible 3. Let me try that again. 3, not much better, but 3 times the term before it, which of course was -18. Now we're starting to get big numbers, so you might go to your calculator. So that's going to be -54. Okay, let's do the fifth term likewise conceptually. So again, now what this says conceptually is the current equals 3 times the previous. Current equals 3 times the previous. So we're going to go 3 times the previous, which is going to be -162. So as a list, this sequence is -2. Starting to get a little sloppy there. And then we have -6, and then -18, -54, -162, etc. Now, I would pause the video right now, and I'll pop up the answers to this third sequence in just a moment. So go ahead and pause, and we'll pop up those answers in just a second. I've gone ahead and already evaluated the first 5 terms of this explicit sequence. Hopefully you're clear on that by now. So this is an explicit sequence, and you compute the first 5 terms. I didn't really show my work. Here's what you should get. So the list would go 4, 1, 16/27, 1/2, 64, 1/25, etc. Alright, let's look at something a little bit more consequential. So now I want to take an explicit rule and take that explicit rule and do things to it. So let me go ahead and do that. Let's erase these hints. So let's look at each one of these sequences and try to turn the list into an explicit rule. Okay, so first thing you want to do is get down some general ideas. I just want to make the point that this lesson is supposed to be designed to make you stronger in terms of your pattern recognition. There'll be easier ways to figure out the explicit rules to these sequences in a couple lessons down the road. But right now we're really just trying to flex our pattern recognition muscles and gain a little bit of mathematical strength. So you'll find some of them are a little difficult. So let me give you some tips in general, and then we'll try to solve each of one of these and find the explicit rule. So here's some general tips. If you notice the sequence appears to have odd numbers in it, that means that you're going to be doing addition. So addition goes something like, well, before I even get to that, let's think a little bit more specifically. So addition. What does addition look like in sequence land? Like if you were taking 4 and adding 4 a whole bunch of times. Well, if you're adding 4 a certain amount of times, then in sequence land that often is going to be called 4 times n, because you're doing 4 a certain number of times, which we'll call n number of times. What if you're multiplying? If you're multiplying, you might think that that's 4 times n, but we've just seen that 4 times n is actually adding 4 a certain n number of times. If you can see in your sequence that multiplication appears to be occurring, then you're going to have 4 times 4 times 4 a certain number of times. So what's that look like? Well, I hope we know from chapter 7 that that looks like 4 raised to the n power, or something like this. An exponential type of sequence. So those are a couple just general tips. So now let's talk about odd numbers. So if you see something that has odd numbers, then the space between odd numbers is 2, right? So you're adding 2 each time. So that's going to be 2n. But if you have 2n and you put 1 in for n, then that's going to be 2, and 2 isn't an odd number. So I think it's really going to have to be 2n plus 1, something like that. Or an odd number sequence could be like 2n minus 1, or it could be like 2n minus 3, etc. So those are all good choices for odd number sequences. The key you'll see to these is experimentation. We're going to be plugging in values to find out if our guess matches the actual sequence we're supposed to be targeting. So experimentation, tenacity are the keys to recognizing sequence patterns. All right, let's get back to it. Odd numbers. Odd numbers. Or excuse me, even numbers. So if odd numbers have plus 1, minus 1, stuff like that, then even numbers, they're even simpler. It's just like 2n, or you could go like 2n plus 2, or you could go like 2n minus 4. There's all kinds of different choices for even numbered sequences, if you recognize even numbers seem to be repeating each other. Okay, let's talk about some other things you might see. How about squarish numbers? Now, of course, squarish isn't a word. You can see them pointing that out, but I'm going to invent squarish to describe things, or let's say, not things, sequences, which contain numbers similar to our squares. What do I mean, numbers similar to our squares? What are the square numbers? Well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36, etc. If you see numbers in your sequence somewhere like that, it's probably an n squared type of sequence, some version of that. Let's move this up a little bit. You could also have a cubish sequence. That's sequences which contain numbers similar to our squares. So what are our cubes? So what are our cubic numbers? Well, 1 cubed is 1, of course. 2 cubed is 8. 3 cubed is 27. 64. 125. 216. Etc. So if you see numbers similar, even if they're not exactly those, it's probably a cubish type of sequence. And the last kind of thing you'll need for our assignment, at least, the only other kind of sequence type thing you might need is a sequence that's alternating. In other words, something that goes from plus to minus to plus to minus to plus, etc. There's a few ways to achieve alternator terms in sequences. I'm just going to give you a couple of those. So what'll work for you is either -1 to the n power or -1 to the n, let's make that a small n, plus 1 power. One of those is going to accomplish whatever alternator term that you need in your sequence. So there's a whole bunch of tips. Let's set those aside. And let's try to, oh, excuse me. I'll just bring it back up a little bit. Oh, if I can. Don't know if it's going to let me do that now. Give me one moment. There we go. Alright, so let's bring that back up here and see which one of those might apply to our problem. So we want to create an explicit sequence for this list right here. So what do we see going on here? Do you see anything that's happening? So you want to take a look at this sequence for a second and see if you can see anything that's happening. I think as we go from here to here, isn't that times 2? Could also be plus 5, but times 2 seems reasonable to me. Then it's times 2 again, then it's times 2 again. Pretty people in class pick this up pretty fast. So I think this is one of those multiplying times 2 numbers. So I think we'll want to think about this kind of thing right here, an exponential sequence. Let's try it out. So we're going to say a sub n, the explicit version, is going to be not 4 to the n, but you guessed it, 2 to the n. But now if I put n equals 1 in, of course that's going to be 2. We want 5, right? We want 5 up here. So I'm going to go ahead and go and do some erasing, get this out of the way, just so we're clear. So I think that's wrong. But it's a good start. It's not really wrong. It's only part of what we need. So powers of 2 is definitely something that's going on here. But I think we also need to work with that 5. So I'm going to put times 5, and now I'm going to try it. N equals 1. If I put n equals 1 in there, what am I going to get? I'm going to get 2 to the 1 times 5. That's 10. If I put n equals 2 in there, then I'm going to get 2 to the 2 times 5. That's 4 times 5. That's 20. If I put 3 in there, then I'm going to get 2 cubed times 5. It's 8 times 5. That's 40. Do you see these numbers over here? Yeah, we do, but we don't see it exactly right. We're supposed to start with 5. So I don't think I have it quite right still, so let me erase my experimentation. So it was really close. In fact, it was all these numbers right here. We just need to back it up by 1. Here's how you back it up by 1. Go n minus 1. Now I want you to try that. Pause the video, experiment, put 1 in, put 2 in, put 3 in, and see, for instance, is the, let's just do a quick experiment. 1, 2, 3, 4, 5, 6. If we put 6 in, we're supposed to get 160. Let's try it. A sub 6 is going to be 2 to the 6 minus 1 times 5. That's 2 to the 5th power times 5. 2 to the 5th is 2, 4, 8, 16, 32 times 5. You can put that in your calculator and you get bingo, bango, 160. That's it. That is the explicit version of this sequence. Let's try one more over here. So this fraction one might scare you to begin with. If you see one with a fraction, you want to take it apart top and bottom separately. So do the top and bottom separately. So on the bottom, we can see it's going pretty easily. It's plus 2, plus 2, plus 2, plus 2. That's, in fact, also the odd numbers. So which one of these versions of the odd numbers down here might work? I think if you experiment for a while, and you might not pick it out as quick as me, it's going to be 2n minus 1. Alright, now the top part of this one's tricky, so are you ready for it? Think about which one of these tips over here is going to provide what we need for the top one. And think about it for a second. Let me go back and erase this for you. Get some of this junk out of the way. What do those top numbers most resemble? Pause the video, take a second. I think they really resemble these guys down here. Think about it. If we go 1 plus 2, we get our 3. 4 plus 2, that's 6. 9 plus 2, that's 11. 16 plus 2, 18. This is the square numbers, or n squared plus 2. Now, so if you're experimenting, you're not going to have it come out as easily as I did this time. So you, of course, want to go and check, once you think you've got an idea, check any term, like the third term, and see if it comes out. So for us, it's going to be this over 2 times 3 minus 1, which is going to be 9 plus 2 over 6 minus 1, which is 11 fifths. Is that my third term? Yes, it is. So this is the correct explicit version of that sequence. There you go. Now, what you want to do now is move on to part 3 of your worksheet. Pause the video and try each one of these. That's what we did in class. Try each one of these, take 10 or 15 minutes even if it takes, and see if you can figure out what each one is. The first one, I will tell you, is very simple. So this one gets 1 check mark. Second one is just about as simple. I'm going to say that's a 1 check mark problem. The third one, you want to think about the alternator, the top and the bottom separately. There's a nice hint, so you should have 3 things. We'll give that one a double check mark. That's going to be more like the level of problems that I'm going to put on your quizzes as we get more practiced with this. So pause the video and give this a shot. So if you've taken enough time, you should recognize for this first problem that we have a really simple linear sequence. So I'm going to say down at the bottom that it's linear first of all. So I'm going to say this guy is linear because that means that we're going to be doing some addition. On the bottom I'm talking about, right here it's going plus 2 each time. You might have also thought of that as evens, even numbers. So a sub n down here is going to be 1 divided by one of those things we talked about for the even numbers. In other words, let me go and erase a little bit more up here. We're going to have the even numbers. So you could go back up there and go ahead and look at your even numbers. But basically it's just going to be 1 over 2 to the n. 2 times n, not 2 to the n. And that's it. If you try a sub 4, you're going to see that it works. You get 1 over 2 times 4. That's going to be 1 over 8, which is just like it should be. Okay. Let's look at the second sequence. This sequence, I think, is also doing something linear. It's going up by 3 each time instead of 2, etc. So if it's linear, then again we're going to have something like mx plus b. Except for us, it's going to be mn times plus b because we're looking at the natural numbers, not the real numbers, x. So I think it's pretty natural that you're adding 3 each time, so you're going to have a 3n. But if you just plug 1 in now, then you get 3 times 1, which is 3. It's not supposed to be 3, it's supposed to be negative 2. So how do you turn that 3 into negative 2? Well, real easy. You go minus 5. You draw a better 5 than that, but a better 5 than that. But minus 5 is going to get what you need. Let's track again. Let's look at the fifth term and see what we get. We're going to get 3 times 5 minus 5 by our formula. That's going to be 15 minus 5. So this is all bad, right? So that's going to be 10. So is the fifth term of our sequence 10? 1, 2, 3, 4, 5. Yes, it's right. So there we go. There's the explicit version of that one. Now 3 is of course a little bit tougher, but you're definitely going to have quite a few problems on your assignment like this, so don't give up on them. This is all about tenacity and experimentation. So let's see. 3 things are happening here, and I'm just going to write up here. We've got an alternator, so I said that's either going to be negative 1 to the n or to the n plus 1. Let's try n plus 1 first. Okay, so that would mean if we have n equals 1, then we'd have negative 1 squared, right, which would be positive. Is the first thing positive? No. Darn it. So that didn't work. This is not going to work. Let's try the other one. Negative 1 to the n power. Let's get rid of all this stuff. So negative 1 to the n power, if we put in, make this into an arrow, if we put in n equals 1 on that guy, then it's going to be negative 1 to the 1 power, which is negative, like it's supposed to be. So I think this guy is what we want to go with. So we know we're going to have a negative 1 to the n in there. Okay, now we want to do the top and the bottom separately. So you now want to get rid of the negative. Forget about this. Just don't even think about it. Don't think about that or that. And the top is like super, super easy. Thinking about it, it's just the natural numbers. N. 1, 2, 3, 4. On the bottom, I think you should recognize something. You might think cubic numbers, because like 27 is a cubic number, but you also should recognize these are all powers of 3. This is multiplication by 3 on the bottom, so it's 3 to the n. So is this our final answer? Let's try it. Let's see. A sub 3. Let me go and fix this guy. Let's get rid of our erasings. We're checking our final answer now. So a sub 3, is that going to be negative 1 to the third times 3 over 3 to the third. That's a lot of 3's. Negative 1 to an odd number is negative. 3 is 3. 3 cubed is 27. Is this our third term? Well, close. We're good with the negative and we're good with the 3, but this is not right. I think we can fix that by saying, well, 27 is in there, it's just here was the 27. So to make this work, I think we're going to have to go plus 1. And you'd want to check that again, but that is the final answer. So there you go. Going from a list to explicit form. The last thing we want to look at in this lesson is something called a fractal. So fractals are a complex phenomena, but they're really based on sequences. And I want us to investigate fractals just to see kind of the power of sequences. And so we can see a lot of application of some of the math we've learned this year with a video in this unit. So we're going to start talking about fractals. Fractals basically just a repeating sequential pattern. This repeating part has more to it than that. For instance, let me bring up a fractal from our class page. So let me go pull up our class page here, and let's go see a fractal that we're going to be studying. So on our class page, we have this fractal right here. You can see that you might not be able to see the sequence, but you can see a repeating pattern. I think as it zooms in, it repeats itself. So we're going to learn more about fractals. Fractals have a lot to do with sequences, and while I'm here, I'm just going to point out that you do have an extra examples video link right here where I do some different kinds of examples if you want more problems, okay? Alright, so that's what a fractal is. So each step in that fractal repeated process, I'm going to use this word probably quite a bit in this unit, so I'm going to use it now. It's called an iteration. Okay, so that's what each step in a fractal process, or a sequence process even, is called. So the only fractal we're going to look at this time today is called the Cantor set. So the Cantor set was one of these fractal beasts or monsters of the 19th century that kind of defied mathematical analysis. Here's how the Cantor set works. First, you just draw a big line. It doesn't really matter how long your line is, but you should try to make it straight, unlike me. I'm bad at straight lines on my tablet thing here. There's a straight line. And now, to form the Cantor set, you take it into thirds. So I'm just going to guess. I'm going to say, yeah, about right there, right there. And for the next iterate, the next step in the sequence, you take out that middle third. So I'm going to cut out that middle part. And then I'm going to do it again. So I'm going to go and cut this guy into thirds, cut this guy into thirds, and for the next iterate, I'm going to take out the middle part. And you just keep repeating this process over and over and over, iterating as many times as you want, imagining that you could iterate to infinity. And you'll notice that on the Cantor set, even if you start out with a really long line, you end up with like little tiny things that you have trouble drawing in no time at all. Even if I started this line going all the way across the screen, I'd still end up with kind of the same thing. So let's count up with a sequence just to reiterate the math we're studying, how many lines there are on each step or iterate. First time we have one line, then we have 2, then we have 4, then we have 8, 16. I'm really going to have trouble drawing the next one, but I think you should be able to guess it's 32. And the next one would be 64, and we could keep going. So I asked how many segments are there for the next 2 iterates of the Cantor fractal set. So I think I was asking you for, in this case, 32 and 64. So let's try to write a sequence pattern for this. I think it's pretty simple to see what's going on, don't you? This is powers of 2 multiplying by 2. So does 2 to the n work? Well, let's try 3. Just see if it works. That's 2 cubed, which is 8. Is the third step 8? This is the third one right there. No, it's not, but 8 is right here. So I think we need to go 2n. Plus 1, minus 1. What's going on? So 2 cubed is 8. So I think we need to go plus 1. Now let's just go and check it again. So with our new one, we'll scratch this out. We're going to have a sub, let's try a sub 4 and see what that is. So a sub 4 for us now is going to be 2 to the 4 plus 1, which is going to be 2 to the 5th power, which is 32. The fourth term, is that 32? No, I still have a mistake in here. So you're going to struggle with this sometimes, and that's why I kind of am making mistakes on this one. So something's wrong here. So if you're watching the video, you're probably gritting your teeth and trying to tell me what I did wrong. But what did I do wrong? So this is not the right one, right? So step 1, I have 1. Step 2, I have 2. Step 3, I have 4. It's going to be 2 to some power. Let's try n minus 1. So now if I try a sub 5, then I'm going to get 2 to the 5 minus 1, which is 2 to the 4th power, which is 16. Is the 5th term 16? Let's go and erase any arrows that I had. Oh, I think I messed it up a little bit there. Oh man, that's too big of an eraser. There we go. 16, is that the 5th term? 1 gets mapped to 1, 2 gets mapped to 2, 3 gets mapped to 4, 4 gets mapped to 8, 5 gets mapped to 16, 5 gets mapped to 16. This is it right here. So there's our expression, our sequence expression for the number of lines in the Cantor set. We'll look at some much more interesting fractals soon enough. I'll see you next time.